Hello everyone and welcome you for today's class. In our previous class, पहली क्लास में हम लोगों ने डिस्कस किया था फ्लो Hagen-Poiseuille equation and flow through pipe. That was a laminar flow, and also we have discussed about flow between two fixed plates. Now today we are going to discuss about turbulent flow, turbulent flow in pipe. Any kind of turbulent flow that we are going to discuss, particularly in pipe, is main area because most of the time you have seen that flow through pipe become turbulent most often because if even it is a laminar flow at the time of entry when fluid enter into the pipe, it becomes turbulent, and after passing through hydrodynamic length, it becomes fully laminar. But whenever conditions are adverse, means any obstruction it find, any roughness or some obstacles, flow again become turbulent. And when velocity is very high, Reynolds number is more than 4,000, 5,000, it becomes naturally a turbulent flow. So, what is the main difference in turbulent and laminar flow? For laminar flow, we have well-established theories to define a flow, to define pressure loss, head loss, and frictional resistances, shear stresses. We can calculate power required, but in turbulent flow, such theories are not available. So most of the theories that are available based on the turbulence modeling prescribed and suggested by many researchers. These are three main prominent turbulence modeling theories, which are one is Boussinesq theory of the eddy current, eddy viscosity concept. Another one is a most universally accepted theory is a Prandtl mixing length theory. This one is the most scientific and most acceptable theory of turbulence modeling, how turbulence is created. And next one is a Von-Karmal. It's a further emphasization of the mixing length theory given by the Prandtl mixing length theory. So first we discuss what is a Boussinesq theory, what Boussinesq suggested. Very likely along the line of the Newton's law of viscosity, he suggested what is a Boussinesq theory. That is number one theory is a Boussinesq theory. This theory about eddy viscosity concept. Eddy viscosity concept. So Boussinesq suggested that turbulent stresses, that because in turbulent flow so many eddy currents forms near the wall surface, beyond the wall surface, because very close to the wall. You see, this is a pipe, and very close to the wall. Here flow is almost laminar. When we go here in this region, flow beyond the a distance y, beyond the distance because very close to the wall, whether it is a turbulent flow or laminar flow is always laminar, very near to the wall. But when we go when effect of wall means boundary layer effect eliminated, then turbulence started. So turbulence means eddy current, means due to formation of eddy current, currents around here, due to formation of eddy current, turbulent stresses that are also suggested by the Reynolds stresses, because turbulence flow, these stresses develop. So turbulent stress is defined by the Boussinesq by equation minus rho u dash and v dash average. Here u dash, v dash are fluctuating component of mean velocity, fluctuating component along x direction and y direction of the velocity, because when the turbulence, then flow will be along x direction, y direction, and z direction. Suppose flow is two-dimensional, then the fluctuating component along x direction, along y direction. So due to these fluctuating component of velocity, turbulence is created, and this turbulence is defined by tau t. T is a suffix, small t is a suffix, and tau t means turbulent stresses equal to minus rho u dash v dash average. It was suggested by equation mu t del u du over dy. ये mu t is a molecular stress, molecular viscosity. Mu t is molecular viscosity. It is not any relation with the viscosity that we have defined in Newton's law of viscosity. In that Newton's law of viscosity, mu, in Newton's law of viscosity, laminar flow, tau equal mu du by dy. So this mu was property of the fluid, but here this mu t, the molecular viscosity, is not a property of fluid, but it is a property of the structure of the turbulence, means type of turbulence, what is the level of turbulence, what is the intensity of turbulence, what is the degree of turbulence. On that parameters mu t is defined. Mu t defined is a molecular viscosity, not a property of the fluid, but it is a property of the structure, means a type of turbulence. And type of turbulence can be defined by degree of turbulence or intensity of turbulence or scale of turbulence. These are parameters by which you can define turbulence. So mu t is not a property of fluid, but it is a property of structure of the turbulence. So that was concept given by the Boussinesq theory of, that is a eddy viscosity concept. And next theory was defined by that is a most acceptable theory, that was Prandtl's number 2, Prandtl's mixing length theory. Here mixing length defined by Lm. Lm is a mixing length. So I want to define, making a parallel concept. What is a mixing length here? Suppose there are two lanes by which cars or vehicles of same kind are moving along the two lanes, and car from one lane moving to another lane, and both lanes, these are two lanes. There are two lanes. These are two lanes, lane 1 and lane 2. Suppose here velocity of all cars. These are cars. These are all cars, and these are all cars of same kind. Here velocity of all cars is 120 km per hour. Here 100 km per hour. Lane 1 and lane 2. Some cars, here suppose this car is moving to this lane and this car is moving to this lane. In this process, equal number of cars are moving from 100 km per hour lane to 120 km per hour lane. So here it will gain momentum, and here when it come from 120 km per hour to 100 km per hour, it will lose momentum but equal quantity, because velocity difference is same. Same concept applied, because when car move from lane 2 to lane 1, it will gain momentum. When car move from lane 2 to lane 1 to lane 2, it will lose momentum but equal quantity, because difference in velocity is same and mass of the car is same. So this concept you can apply by using analogy in mixing length theory. In flow field, suppose in flow field there are two layers. There are two layers, layer 1 and layer 2. Here velocity is u plus u dash. Here velocity is u. In layer 1 velocity and fluid is moving from here to here. We take this is area dA. And from this fluid is moving like this, from layer 2 to layer 1 and layer 1 to layer 2 from area dA. Suppose rho is density of the fluid, and because it will move up from layer 1 to layer 2 with velocity fluctuating component v dash, and it will also come down with fluctuating component v dash, because when it will move upward from layer 1 to layer 2, you can make here diagram, velocity profile here like this. Here velocity is u and here velocity is u plus u dash, and fluid is moving from layer 1 to layer 2 with velocity, fluctuating component velocity v dash, and moving from up to down with fluctuating component velocity v dash. So mass of fluid, how much mass of fluid moving up from layer 1 to layer 2? Mass of fluid. Let us minimize it. Mass of fluid from layer 1 to layer 2. What is the mass of fluid moving from layer 1 to layer 2? From layer 1 to layer 2, how much mass is moving? Mass transfer. Mass transfer from layer 1 to layer 2, layer 1 to layer 2 equal to rho v dash dA. dA is area through which mass is moving from layer 1 to layer 2. This is area. And rho is density of fluid, and v dash is the fluctuating y component, because it will move along y direction, x direction and y direction due to velocity v dash component. So momentum change, momentum gain of fluid equal to rho v dash u dash dA. Because u dash is a velocity difference between layer 1 to layer 2. Layer 1 to layer 2 is a velocity, this length is Lm. This is a mixing length Lm. Between two layer distance is Lm, that is a vertical distance Lm. So this is the momentum gain of the fluid that is moving from layer 1 to layer 2. And same thing because flow is continuous, and layer 2 to layer 1 same mass of, because to maintain continuity, same mass will move from layer 2 to layer 1. So mass gain, momentum loss of fluid moving from layer 2 to layer 1 equal to rho v dash u dash dA. Because same, under continuity equation, same mass is moving from layer 1 to layer 2, same mass is moving from layer 2 to layer 1, and velocity change is same. U dash is a difference in velocity between two layers. So change of momentum, here momentum gain, here momentum loss. So total change of momentum. Total change of momentum is equal to sum of the, because total change in momentum of fluid equal to rho v dash u dash dA minus again rho v dash u dash dA equal to 2 rho v dash u dash and dA. This is a rate of change of total momentum of the interchange of fluid from layer 1 to layer 2 and from layer 2 to layer 1. And this rate of change of momentum equal to force applied. And this force applied equal to, this force is cause of the development of the shear stresses. This equal to 2 rho v dash u dash dA equal to shear stresses, turbulent shear stresses will develop due to interchange of this fluid from layer 1 to layer 2, layer 2 to layer 1 equal to 2 times into dA. Now dA will be replaced. So tau T equal to rho u dash and v dash. This is the equation of the turbulent stresses that was defined by the Prandtl mixing length theory. But Prandtl also assumed that both component u dash equal to v dash, approximately equal to. He assumed that fluctuating component along f direction, y direction are approximately same, and we consider it is equal to u dash. So this equation will further modify a rho u dash square. Tau T equal to rho u dash square. So tau T equal to rho u dash square. Now writing tau T, shear stresses, turbulent shear stresses equal to rho and u dash square. This is equation number 2 for the Prandtl, according to Prandtl mixing length theory. Now one thing here I want to define that u dash, because you know that a u dash velocity from a u to u plus u dash. So u dash, you can write u plus u dash equal to u plus del u over del y into Lm. Because u is a function of y, u is a function of y. As we move up, velocity is increasing, so u dash, you can replace u dash equal to del u over del y into Lm. This u dash is equal to del u by del y Lm. You can write, because u is a function of y, you can write it in exact differential, that is equal to du by dy into Lm. Putting this value of u dash in this equation, so tau t equal to rho Lm square du over dy whole square. This is equation number. This is a general equation described by the Prandtl mixing length theory. If we compare both equation, Prandtl mixing length theory and Boussinesq theory, equation derived by Boussinesq theory, because both are turbulent stresses. According to Boussinesq theory, tau t equal to mu t du by dy. So by comparing equation, this one, that was equation 1. By comparing equation 1 and 3, we can find out what is a value of molecular stress, molecular shear, molecular viscosity. So mu t equal to rho Lm square du by dy. Du by dy. This is a concept of molecular viscosity. So you can see molecular viscosity is a function proportional to rho density and square of the mixing length, and proportional to spatial derivative of the temporal mean velocity. U is a temporal mean velocity, because mean velocity is average of the fluctuating velocity, average of the instantaneous velocity, that we will discuss separately. So this is a mu t, molecular viscosity. These are two equations that we have derived. Let us here again, one thing I want to find. According to Prandtl's experimental observation, he defined that mixing length Lm is proportional to y. So Lm was equal to ky. K is a factor depending upon the type of the material, kind of the turbulence. So he found by experimental observation, K was equal to 0.4. For turbulent flow, in pipe K was observed. This value may vary depending upon the type of turbulence and nature of the material. So this is equation, and y is the distance from the wall. It is distance from the wall, because we measure distance from the solid surface. If flow is from the pipe, then y is measured from the pipe solid, where velocity becomes 0, because when fluid is come in contact with the any kind of fluid, any type of fluid, when coming into contact with surface, by concept of no separation theory, it will become 0 velocity, and turbulence and shear stress also become maximum for laminar flow. But turbulent stresses, when there is a turbulent stresses are much larger compared to laminar stresses. That's why when there is a turbulent flow, laminar stresses are neglected for long pipe. So this is the concept given by the Prandtl. This equation is very useful. And now further theory is Von-Karmal. He is also researcher. Von-Karmal theory of mixing length similarity. He further emphasized over this equation that was derived by the Prandtl mixing length theory. He said that mixing length is proportional to ratio of. Now let us define Von-Karmal theory. Third one is a Von-Karmal theory. Prandtl given theory that was mu t equal to rho Lm square du by dy whole square. That was given by the Prandtl. So viscosity, that is a molecular viscosity given by the Prandtl was equal to, sorry, not molecular viscosity, it is a turbulent stresses. As suggested by the Prandtl mixing length equation tau t was equal to rho Lm square du by dy whole square. That was given by the Prandtl. And according to that one tau t, this mu t was rho Lm square du by dy. That was molecular viscosity. That was molecular viscosity as suggested by the Boussinesq theory. So this was a equation given by the derived by the Prandtl's mixing length theory. Now third suggestion is Von-Karmal theory. He further emphasized Prandtl mixing length. He suggested that mixing length Lm is proportional to ratio of du by dy to second order d square u by dy square. This ratio means the mixing length is proportional to first order derivative of du by dy to the second order derivative of du by dy, and that Lm was equal to, if you remove proportionality you get K, a characteristic constant that depend upon the material and type of the turbulence, material of the pipe and type of the turbulence, that is equal to du by dy upon d square u upon dy square. So putting this value of Lm in the equation given by the Prandtl mixing length theory, so tau t, turbulent stresses will become rho into k square du by dy whole square into du by dy whole square upon d square u by dy square whole square. Further simplifying, you get rho k square du by dy power 4 upon d square u by dy square whole square. This one is a correct equation given by the Von-Karmal. If you find the result comparing all three equations and you get constant k or mixing length from these two equations, you will get almost similar, because these are all three equations when combined together are give you very practical values that we want to calculate on the basis of turbulence modeling. Whether equation we use Von-Karmal equation or Prandtl mixing length theory, or by using Boussinesq theory, we can calculate by using Boussinesq theory, because he first suggested turbulent stresses. We can find turbulent viscosity, that is known as molecular viscosity. So I think these equations will very help you, because Prandtl mixing length theory is very important, and in most of the competitive examination, particularly I have seen one question in previous year in 2024 was asked to define mixing length theory based on the Prandtl mixing length theory. So most of the time you will get questions in this topic, and this is also very useful, because theoretically well-defined theories that are not available, and these theories are based on the modeling and experimental observation. That's why these theories are very important to understand the nature of the turbulence and the nature of the turbulent stresses, also known as the Reynolds stresses, that we have to define for finding out the pressure loss occurring in turbulent flow, because turbulent stresses are much larger compared to stresses due to laminar. Means that turbulent stresses tau t much larger compared to tau laminar. That's why these theories are very important in practical engineering calculations. So thank you very much for watching my video lecture. I wish you Please suggest any suggestion, any comment, anything that you want to require, and we will solve one question tomorrow and next day that based on the all three equations, all three theories. So that will make your concept very clear when you solve one question. Thank you very much, and please like and subscribe.